Notes on limits at infinity. There are some basic limits at infinity at the top here, just some things that you do need to memorize. So I'll draw a picture for the first one here. So if you have a limit as x approaches either positive or negative infinity of 1 over x, it's going to equal 0. Now, if you're wondering why, well, here's the graph. 1 over x. And I'll make some asymptotes in here because, well, they do belong. So let's see here. If I go out to positive infinity, I'm approaching 0, that asymptote. If I go out to negative infinity, I'm also approaching 0 at that asymptote. So that's why a number over infinity essentially is going to give us a 0 value. Next one you're going to need to memorize here. This one's a little weirder and trickier. If you already took AB, you probably have not seen this. But if you have this function 1 plus 1 over x all to the x, that as you go, the end behavior is actually equal to e. All right. Now you can play around with it. It's like if I put a number in front of the x right there or right there, like for instance, if I put like a 2 in front of there, that'll be e squared. Or if I put like a actually, no, that'd be e to the 1/2. If I put like a 2 on top, that would be e squared. But we're going to tackle a problem similar to that in the back here in a moment. And then just knowing what arctan is, I sketched this in a previous video. It's on the archives, but this is what arctan looks like. It's this function right there, and it's got 2 horizontal asymptotes. Okay. Bottom one is negative pi over 2. Top one is pi over 2, so that's why that those limits are what they are. Okay, so those are just some that you need to know. Definitions of vertical asymptote and horizontal asymptote. I know that previously in pre-calculus or algebra 2, they told you how to find vertical asymptotes, and it wasn't the definition though. So this is the actual definition. If you're asked to find a vertical asymptote using the definition, find a horizontal asymptote using the definition, it's going to be about this right here. So the vertical asymptote just says that if you're approaching a number from the right or the left, it doesn't matter. That's why there's an or, from the right. And I think this is kind of hard to read. So this is the positive one right here. This is supposed to be a plus, and that's supposed to be just a minus. So if you're approaching it from the right and you get either positive or negative infinity, or the left negative positive infinity, then that's a vertical asymptote. And for a horizontal asymptote, if you're going out to infinity, or if you're going out to negative infinity, you get a number, that would give you your horizontal asymptote. That one on the bottom here, I know we've talked about before. All right, now let's talk about how fast some of these things are growing. So if you're evaluating a limit as x goes to infinity or negative infinity of the ratio, that means ratio means dividing, of 2 functions, you need to consider which one overpowers the other function. So if you have a function on top that grows faster than a function on the bottom, well then it's going to go to infinity because that top one is so much larger as you get further and further up to infinity. But let's flip it. Let's say that your bottom one is a lot faster than your top one. Then it's going to go to 0. Okay, so right here is, this isn't every function in the world, but these are the ones that we need to be most familiar with of rate of growth. So this is the slowest growing one, is some ln function, and then some x to the whatever function, and then ln evolve with an x, and then start building on from here. So you can see that you still have an x, but you're adding 2 different parts. You get exponential, you get factorial, and you get x to the x. That's the biggest one right here. So, and this is kind of what I said right here, how the bottom one is faster, says f is faster. So if the bottom one is faster, you go to 0. Top one is faster, you go to infinity. Okay. So let's go ahead and look at, sorry about that, some of these problems. I'm going to do just a little bit out of order here. I'm going to start with this one right here because if I do the first one, it might be a little confusing. So what you want to do here is you have a power on top and a power on the bottom. They're actually growing at the same rate. They're both x. Okay, top one's growing at an x rate, bottom one's growing at an x rate. So And I'm looking really at the parent function. I know one has a 3 in front, and one has a 6 in front, and that'll come into play as you get the right answer. But if I'm looking just at the parent function itself, it's growing at a rate of x. So what I want to do here, since they are the same, I need to play around with it a little bit. I'm going to multiply by 1 over the highest power, or the highest, I don't want to say highest power necessarily, the highest rate of growth. Okay, so in this case, I'm going to multiply the top and bottom by 1 over x. And that's each term that's going to get pushed into. Okay, so for the next step, when we get limit as we go to positive infinity, I don't need the plus sign because it's just assumed it's positive infinity, but there's not there. I'm going to get 3x over x plus 5 over x all over 6x over x minus 8 over x. So some things I'm going to start simplifying here. So we're going to get those x's to cancel out right in front. So I'm left with the limit as x approaches infinity of 3 plus 5 over x all over 6 minus 8 over x. Now what happens since I have the x on the bottom for these individual terms? So I have a 5 over x. If I plug it in infinity, that's just going to zero out. Since I have an 8 over x, if I plug in infinity, again, the bottom's going to grow faster. It's going to zero out. So I really have 3 plus 0 over 6 minus 0. So I'm going to get 3/6, which reduces down to 1/2. I don't need to write the limit right here because I'm essentially plugging it in right here. So I'm good to go. So my answer right here is just going to be 1/2. Now, so there are some tricks that your teacher may have taught you last year about, oh, well, you do this, but that doesn't always apply. And I'm going to give you an example just down here on why it's not always, oh, you just take the highest power and you just compare those. I think it's Bobo Botten, my worst enemy here. They just, oh, the coefficients divide. Well, let's create a very special situation here. So I'm just going to create an extra example. So let's say that we have the limit as x approaches infinity of e to the x plus x to the third all over 2x to the third minus e to the x. Okay? This is kind of where that Bobo Botten would give you an answer of something that's wrong. Okay, stick by the rules of divide by the fastest growing function here, parent function actually. So what's the fastest growing function on the top and bottom? It's actually e to the x. So I'm going to multiply everything by 1 over e to the x. So when I do that, I'm going to get e to the x over e to the x minus x cubed over e to the x all over 2x cubed over e to the x minus e to the x over e to the x. So what's going to happen here? E to the x over e to the x gives me a 1 minus e to the x is faster on the bottom. That's a 0. And on the bottom, I'm going to get a 0 minus a 1. So I have 1 minus 0 on top, 0 minus 1 on the bottom. It's going to give me 1 over negative 1, which is negative 1. Okay? So this is why this trick always, not only, it's not a trick, it's what you're supposed to do. It always works by multiplying by 1 over whatever the highest power is. All right. Let's get to some little different guys right here. So we're going out to, it says positive, negative infinity. So it's not going to come too much in play here because I'm dealing with square roots and squareds. Not too worried about that. I'm actually going to do the positive infinity one first because this actually really is 2 problems. So I'll do the positive infinity one first. So what I'm going to do here is, I'm just going to write this over here just so it's clear I'm doing the positive infinity one first. All right, so I need to find the highest power. Now you'd think that the top one's the highest power, and I hear the lot, oh, it's x squared. What's over the x squared? It's a square root. What's the square root of x squared? It's x. So the highest power on top is an x. What's the highest power on the bottom? Also an x. What's my highest power? It's x. So as I go through this, I'm actually going to multiply this by 1 over x. Now I can't just multiply an x right here on the square root, because you got to be able to push it in. So do you agree that x is the same thing as square root of x squared? And the bottom one is multiplied by 1 over x. These two statements are equivalent. Okay, so now I can push that in. So I'm going to do the limit as x approaches infinity, square root of x squared over x squared plus 2 over x squared all over 3x over x minus 6 over x. All right. So what's going to end up happening here is I'm going to get this to be a 1. This is going to be a 0. This is a 1. And this is a 0. So I'm going to get the square root of 1 on top, which is 1 over 3. Now I'm going to do this from negative infinity. And what's going to be happening here is I'm going to start looking from end behavior on the left-hand side. So, for instance, when I start looking at this x right here, I'm actually multiplying by 1 over root x squared and 1 over absolute value of x. Where'd that come from? Well, these two statements right here are equivalent when we're going out to positive infinity. All right, so I'm going to positive infinity. Do I really need the absolute value? No, I don't. Going to negative infinity, I do need that absolute value because the square root of x squared is an absolute value. That's what it is. This will always be positive, and then so this will always be positive. So what's going to end up happening here is since I'm going out to negative infinity, I'm actually going to be using the negative x. So this is going to become x squared over x squared plus 2 over x squared. Since I'm going out to negative infinity, this is going to be 3x over negative x minus 6 over negative x. Okay? Because I'm essentially going to be multiplying the negative x through since I'm going out to negative infinity. Now, if this was an x squared, don't worry about it. Okay, only if it's an odd power. So first, third, fifth, then we really care about that negative right there. Okay, so what's going to end up happening here is we're going to get an answer of negative 1/3 when you go through the rest of it, if I can't figure everything out. All right. Next one, sorry, this kind of went away right there. So this one looks just like this formula that we did right here, except the difference is we have a 2 on the bottom. I like to rewrite that as 1 plus 1/2 1 over x to the x. So like I said, whatever the coefficient is in front of this makes that, it is the power. So what's the coefficient in front? It's a 1/2. So this is e to the 1/2, which is the same thing as square root of e. If this was a over 3x, it'd be e to the 1/3. If this was 4 over x, it'd be e to the 4th. So just know how to play around with that formula a little bit. Looking at the time right now, I'm going to speed this up just a little bit. Okay. Let's look at this function right here, this example right here. I hit an exponential and then a factorial. Exponential on top, factorial on bottom. It grows faster on the bottom, so this is actually going to be equal to 0. See, told you go through this a little faster. We get to the vertical asymptote part last. For the sine one, what's the end behavior of sine? So essentially, sine looks like this. And it's going to keep doing this over and over and over and over again. So since it goes up and down, it oscillates. So this is going to be a does not exist. All right. Last one here is just finding vertical asymptotes using the definition. So for this one, we can use our math skills we learned before to figure out what the asymptote should be, but then we're going to have to put them in the form of the definition. So to find a vertical asymptote, it's if the bottom of a fraction is equal to 0, it's a vertical asymptote. So I'm going to get x to equal plus or minus 1. But I have to use the definition for a vertical asymptote. If you remember, that's when I do the limit as x approaches 1. Either, it doesn't matter, it has to go from the right or the left of this function, and I have to do the limit as x approaches -1. Doesn't matter, right or left. I'll just pick both of them right just for, doesn't really matter. For this problem of this, I'm going to call this f of x just to help me out a little bit here, speeding things up. So as I go to the right of this, you can just plug in like a 1.1 just to see if it's going to be positive or negative. So if I plug in like a 1.1 on the top, it's adding, and so it's going to be positive. So the top is positive. For this one, I'll just do the side work over here. So it's positive on top. If I plug in a 1.1 on the bottom, I'm also going to get positive. So this is going to give me a positive infinity. So that verifies the vertical asymptote at 1. And if I go -1 to the right, which would be like 0.9 or -0.9. So if I do a -0.9, is that going to give me -0.9 on top? That's going to make that positive. You know what? I'm going to factor this one up here to make my life a little bit easier. All right. So if I do a -0.9, I'm going to get -0.9. So negative times negative. Or no, sorry, negative times positive, which is going to be negative. And the bottom one, if I do -0.9 and I square it, I know that's going to give me something that's less than 1, so it's going to be negative. So negative and negative gives me a positive. So that right there is going to verify my vertical asymptotes. Sorry, I knew this one was a little bit on the longer side, but just want to go through it nice and thorough. It can be a confusing topic, so I'm glad I covered it a little bit more in depth than I have in previous videos. All right.